Amy Hyde, Editor-in-Chief of Pumps and Systems Media. Welcome to Tips and Tricks for Driving Better Pump Performance, sponsored by Uniblock Hygienic Technologies. Our presenter today is Eric Soderstrom. Eric specializes in assisting customers find optimal sanitary pumps, strainers, and valves for liquid transfer applications across various industries, with a strong focus on food processing, meat and poultry, and food-grade tank transport. Eric joined Uniblock Hygienic Technologies in 2009, and he has a bachelor's degree from the University of Georgia. At this time, it is our pleasure to begin the webinar. Stay tuned after the presentation for the Q&A session, and please send your questions through the Ask Question box, and we'll get to as many of them as possible. Now I'll turn it over to Eric to begin the presentation.
Thank you, Amy. Hello, everybody. Glad to be here. My name is Eric Soderstrom. I am Business Development Manager for Uniblock Hygienic Technologies. I have been with Uniblock for 16, going on 17 years now, and have rather extensive knowledge dealing with successful and both challenging pump applications. Over the years, I've been lucky enough to work with some of the best problem-solving engineers in the business, and they've taught me a great deal about pumps and pump performance. I hope to share some of what I learned with you all here today. So if you're not familiar with Uniblock, we are a pump manufacturer headquartered here in Kennesaw, Georgia, specializing in stainless steel hygienic pumps. We've been in business for nearly 40 years now and have products in thousands of plants globally. The presentation here today will focus primarily on rotary lobe style pumps, as well as AODD style or air operated double diaphragm pumps. We find these to be some of the most common pumps in sanitary applications. That said, the topics covered are relevant for many other pump types as well. So the webinar takeaways, I want to help today with how to identify underperforming pumps in your plant, operational tips to optimize pump performance, feature and technologies that improve product safety, uptime, and operational efficiency, and a clear action plan when selecting or upgrading your legacy pumps. So you are under pressure to perform. Businesses need to produce more and more and at lower costs. And guess what? Pumps can be a major impact on that. So you and your business are under pressure to perform. Businesses need to produce more and more and at lower costs. And guess what? Pumps can have a major impact on that. A pump is the heart of a process line. It's a critical component. If the pump has issues or fails, an entire line can shut down. Downtime, as we know, is costly and is often measured in minutes, not hours or days. For example, a food plant might have 50 workers downstream of the pump. If the pump has issues and if the line stops, so do the workers. Pump performance is mandatory. Luckily for us, there are some tips, technologies, and pump improvements that can increase performance and reliability. So how do we identify underperforming pumps? Most of the time, it's identified by a decrease in flow rate or pressure of the pump. This is normally caused by wear and tear, but it could also be caused by a change in the product. Are you pumping a thick product on some runs, and are you pumping a thin product on others? As well as piping changes. Sometimes it has to do with the high cost of maintaining or keeping that pump running. This is often due to frequent remachining from heavy wear. So frequent remachining is a big indicator, as well as seal leaks. The most obvious is the pump leaking all the time. But it could also be excessive noise and vibration coming from the pump. These are all indicative of underperforming pumps. So how do we define performance? What do we mean by is a pump performing? Performance is measured in many different ways, but typically it has to do with flow rate. Is your pump keeping up? Can your pump hit the flow rates that you need it to? And secondly, just as important, can it hit the pressures? Is the pump generating enough pressure for your process? But longevity is also a big one. Is the pump lasting, or do you need to replace it or remachine it often? We had a customer who said his favorite pump, which one he had for 12 years, and he had never changed the seals on that pump once. So for him, seal life was a definition of a performing pump. But in reality, it's a little bit of everything that you see here. It's all these intertwined. So there are many factors that impact a pump's performance. And the big one, which is why it's in red here, is wear and tear on the pump. Wear and tear drops the pump performance. That is guaranteed. But there's also pump size. Is the pump sized correctly for the application? Are you running the pump too hard? Is the pump operating at its optimal levels? There's viscosity. Viscosity has a huge impact on a pump performance, but it also has an impact on the pump's inlet and discharge pressures. Then there's, of course, changes in the supply or discharge piping. All these have impacts on pump performance. But let's focus on the wear and tear first. This brings us to the golden rule of pump performance, and that is to maximize pump performance, you must minimize pump damage. Again, to maximize pump performance, you must minimize pump damage. So what is causing wear and tear on the pumps? Well, the majority of pump damage doesn't occur because of pumping. It occurs from the cleaning and sanitation of the pumps. Pumping is actually pretty easy. Overcoming the rigors of daily cleaning is not. Sanitation crews are notoriously rough on equipment. There is actually a saying, give sanitation crew members an anvil and they will find a way to break it. That's obviously an over-exaggeration, but I have personally seen sanitation crews use hammers, wrenches, and channel locks to pull the pumps apart for cleaning. Heavy tool use, poor handling, all this leads to dings and dents on your pump. And dings and dents lead to performance loss. Then there's pressure. Too much pressure can cause the shafts of the pumps to deflect, leading to metal-on-metal contact. And that, of course, leads to performance loss and even seal leaks. There's foreign material. Foreign material is anything that shouldn't be in the process stream. Foreign material is more common than you think, and it leads to major issues. So to keep a pump performing, you need to keep it from getting damaged on the inside. More on this later. Let's talk about choosing the right size pump for success. When you go buy a car, you don't go choose the car because the speedometer says it can go 140 miles per hour. And you certainly don't drive it that fast. We all know cars run best at 55 to 60 miles per hour. It's the same for pumps. Pumps operate best in the middle of the road, so to speak, of their capabilities. Yet this happens from time to time. A customer spec'd a pump on its theoretical max flow capacity. Customers say needed 70 gallons a minute, for example. However, after they got the pump and installed it, they're only getting 40 gallons per minute. The reason for this is that products and pressures dictate the speed that you can run the pump, and therefore the pump size that you should get. Generally, speed kills, and this is often true with pumps too. So a tip, when in doubt, go bigger and run the pump slower. Stay in the middle of the road of that pump's capabilities. Here is an example of product dictating the pump size and operating speeds. All these pumps shown in this picture here are well suited for 10 gallons a minute. The small pump on the left is perfect for a water-like product, and it can run at higher speeds, easily hitting 600 RPM. The pump in the middle is well suited for creams or lotion, which is thicker, shear sensitive, so it runs at lower speeds, and therefore a larger pump, say around 300 RPM or so. And lastly, you have the behemoth pump here, used for chicken breasts. Chicken breast is extremely viscous, and it requires a much larger pump and a much larger inlet, and it runs at very low speeds, often as low as, say, 20 RPM, to preserve product integrity. So size your pump for longevity. Here you can see two pumps that both have 1.5 inch connections. As indicated by the red arrows, the pump on the left is operating right about at max capacity. The pump on the right is running much lower and is in, quote, middle of the road, so to speak, of its capabilities. The longevity of a pump running at 400 RPM versus one running at 900 RPM is significant. The slower pump almost always has longer lasting seals and less wear. Sometimes pricing between pump sizes urge buyers to consider buying the smaller pump, but the savings are almost always lost on the maintenance costs shortly thereafter. So when in doubt, again, go bigger, especially as product viscosity increases. So product viscosity plays an important role in pump performance. Both lobe and gear pump efficiency increase as product viscosity increases. For example, if you're pumping 10 gallons a minute of water at, say, 30 psi, the pump is running at 600 RPM. That same pump doing 10 gallons a minute of honey, which is thicker, at the same pressure, only runs at 350 RPM. So why is this? This is due to what we call slip. Slip in a pump is when the product basically can't overcome the discharge pressure and it just kind of slips back and forth inside of the pump rotor housing. Now, how can slip be a performance problem? Well, let's say you're running multiple products with multiple viscosities with the same pump. This is pretty common in plants. Now, if your gear motor is sized for, say, the honey at 350 RPM, then you may not have enough power or speed to hit the 600 RPM required for the water. This will appear then like the pump isn't performing, when in reality, it's the gear motor's output speed that is limiting flow. So generally speaking, as viscosities increase, the pump performance increases to a certain level. Now, as viscosity gets higher and higher and higher, you start having other issues that arise. And these include infeed, or the pump suction side, and discharge pressure. Let's talk about pump infeed and yet another golden rule. And that is as follows. The pump needs to receive the product before it can pump it. See, most pumps are designed to push, not pull. Some pumps do provide suction, like AODD pumps and some screw pumps, but generally, you want to make it as easy as possible to get the product into the pump. And I'll give you an example. The picture here shows a nice, delicious milkshake. Now, notice the straw that they put in that milkshake. It's a relatively short and oversized straw. Now, what would happen if they gave you a coffee straw there instead? What would happen is you wouldn't get any milkshake into your mouth. You would pull and pull and pull, and you wouldn't be able to enjoy that milkshake. So instead, they gave you an oversized straw to make it as efficient as possible to get that milkshake into your mouth so you can enjoy it. It's the same for pumps. You want to make it as efficient as possible to get the product into the pump so it can pump it well. So how do you ensure a proper pump infeed? You want to make sure you have the proper inlet size. Generally speaking, bigger is better. For example, don't feed a 3-inch pump with a 2-inch pipe. You want to avoid bends in the pipe, and you want to try to keep it as short and straight as possible. Now, I have an example here of a food plant that we had sold some pumps to, and they called us saying they were having issues. They were having seal leaks and poor pump performance, poor flow, really. And when we got there, we noticed that they had a 6-inch pump, and they were feeding it with a 4-inch line. So what we did is we just simply told them to increase the infeed pipe from 4-inch to 6-inch. And guess what? It resolved the problem. They got much better pump flow, and the seal leak issue was resolved. So the tip here is make sure you can get the product to the pump easily. Make pump infeed easy and efficient. Here is a nice diagram about optimizing pump inlet piping. So the focus here is on the pipework feeding the pump. This is an actual example of where we resolved a pump performance issue for a customer. The issue was low pump flow rate. The conventional AODD pump on the left had several infeed issues. You have long pipe, you have bends, in this case 4 90-degree elbows, and you have a small pipe diameter. So to sum it up, you have 6 feet of piping, 6 feet of 1.5-inch piping. Again, think coffee straw for your milkshake here. The diagram on the right is an alternative AODD pump. And you note here it has straight and short piping, straight from the supply tank to the pump. And we increased the pipe diameter from 1.5 to 2-inch. Much more efficient pump infeed, and the pump performance issue resolved. Signs of poor pump infeed are basically no flow, sometimes low flow or variations in flow, and even cavitation, so like a very loud knocking sound in the pump. So to sum it up, basically if the pump can't get the product, it can't pump it. Understanding high discharge pressure and your pump. Pressure on your pump increases as pipe length and or viscosities increase, and this can cause pump wear. Long discharge pipe length increases the pressures on your pump, and higher viscosities along with long pipe length need special attention. You really want to consider relieving the pressure whenever possible, and you can do this by upsizing the pipe diameter. This will lower pressure on the pump and improve performance. It can also minimize wear and improve seal life. We have an example of this at a poultry plant. We had sold several large 6-inch pumps, and they had contacted us about one of them that was having excessive wear issues and constant seal leaks. Upon visiting their plant, we noticed that all their pressure gauges were blown out. They were all maxed out, indicating extreme pressures on the pump. The product they were pumping was a very thick, 27-degree, partially frozen chicken mixture used for a chicken nugget line. Again, they were using a 6-inch pump, but we noticed that the discharge piping was reduced down to 4-inch piping, about 25 feet, if I recall, of 4-inch piping. We recommended upsizing the discharge piping to 6-inch, and this resolved all their pressure spikes. It fixed the pump wear issue, and it fixed their leaking seals. Larger pipes decrease pressure, and lowering pressure on the pump can improve performance, minimize wear, and improve seal life. Here is a nice diagram indicating the relation between pipe diameter and discharge pressures. What you have here is a sample syrup line, 40 gallons a minute, 100 feet of piping, and a 2,000 centipoise viscosity. If you look at that 2-inch pipe, it has 177 psi of pressure. If you were to upsize that pipe to a 3-inch pipe, you have an exponential drop in pressure. It gets down to 32 psi. The difference between a pump operating at 177 psi and one operating at 32 psi is a difference between one lasting 10 months or 10 years. We always ask about discharge pipe diameter when specifying a pump, and this is the reason why. Larger pipes lead to better performance and longevity. We have another example here actually of a tomato paste application. We sold one of our AODD pumps on a drum unloader to unload tomato paste. This pump was a 3-inch pump, and when we delivered it to the customer, they started it up and it ran great for 2 weeks. On the 3rd week, we got a call from them and they said the pump just stopped working. After digging into this a little bit, we come to find out they had changed the piping on the discharge side of the pump from 3-inch and put in a 2-inch pipe instead. This drastically increased the discharge pressure on the pump to the point where the pump just couldn't overcome the pressure anymore and it stopped pumping. We went back to the 3-inch pipe, it drastically reduced the pressure, and the pump went back to performing great. Signs of excessive pump discharge pressure include heavy pump wear, constant remachining to keep the pump tolerances in performance. This is a big one. Poor flow rates, and of course, constant seal leaks. Improving seal life. Seal leaks are the most visible form of pump issue. They are considered hazards and pose a risk to workers and product safety. Leaking seals need to be addressed. So what causes seal leaks? Well, we've talked about most of the reasons why already. Excessive pressures and or pump speed, poor maintenance, mishandling during cleaning, that's a big one. Pump cavitation, if the pump isn't getting enough product, it can vibrate and cause seal leaks. For material, is there something in the product that shouldn't be in there, metal, glass, etc.? Or even the wrong seal type for the application. And that brings us to improving seal life. You want to make sure you're using the correct seals. Just because a pump is using a certain seal doesn't mean it should be. And I'll give you an example of this. We recently visited a food manufacturer that was using a legacy honey pump. They were replacing the seals in this pump weekly at $2,000 a pop. Plus, the seals were costing the customer over $200,000 a year in lost product. These are all signs that the wrong seals are being used. If this sounds like you, talk with a pump specialist about seal options. I'll give you another example. cheap seals versus the right seals. We had a customer in the tank transport industry that was pumping vinegar. Vinegar can be a pretty challenging product, especially on seals. They were using cheap O-ring seals that were leaking every 2 weeks on average. And each time the seal leaks occurred, it would cost the customer about $3,000 in downtime, labor, etc. We recommended a different type of seal altogether, and this ended up lasting 14 times longer, saving the customer tens of thousands of dollars per pump. And this is important because this customer has over 500 pumps. Massive savings by using the right seals. The right seals mean big savings. Another great way to improve seal life and minimize pump damage is eliminating foreign material from entering your pump. What is foreign material? Well, it's essentially anything that shouldn't be in your process stream. Common foreign material include metal in the form of nuts, bolts, weld beads, glass, plastics, bone, rocks and sand, and even undissolved ingredients like lumps of salt, for example. Strainers protect the pump from foreign material. I have an example of this. We had some customers, a customer actually in the poultry industry, that was complaining about the seals leaking on irregular intervals and the pumps were locking up. Upon inspecting, we found that metal pieces of belt wire were entering into this pump, causing some serious damage. Having a strainer in this situation protects the pump. It keeps the metal and foreign material out of the pump before it causes damage. It's often said a strainer pays for itself the first time it catches foreign material before entering the pump. So a strainer can be a valuable asset. Strainers don't always work at protecting the pump though, because you can't always use them. They do perform best with thinner products. For example, like a water or a vinegar or an alcohol. You get it. Thinner products perform better. You can't really put a strainer in a line where you have chili, for example. So why do legacy pumps fail? Well, the number one reason they fail is because they're based on just old designs that are not optimized for their environment. Just because a pump has been in service for 20 years doesn't mean it performs as well as it could. There are newer technologies available to improve pump performance, capabilities, and longevity. Why legacy lobe pumps fail? Typical CIP capable pumps don't work well in COP applications. Remember, COP is manual cleaning. Manual cleaning is the leading cause of pump wear. Some CIP pumps also need their rotors removed before CIP, increasing the wear. Many pump styles utilize long shafts that tend to deflect more under higher pressures or more viscous products, and this causes excessive wear. Rotor materials made from soft alloys may increase wear and require expensive remachining or replacement to maintain the performance. A typical pump has 2 rotors, 2 rotor bolts, 2 lock nuts, and this often leads to torquing errors. And last but not least, old rear loading seal designs require pump housings for removal, and this is labor intensive and cumbersome. More modern, updated pump technology is designed to simplify the sanitation process. Remember, pump sanitation is where most damage occurs. So newer pumps are designed to simplify the pump sanitation and reduce damage. They work well in both CIP and COP applications. They offer tool-free disassembly. This reduces dings and dents for less wear. They are typically short and stout pumps, which offer higher pressure capabilities with less shaft deflection. The harder rotor material wears less than the conventional alloys, and the parts are designed for one-way reassembly, avoiding parts damage during cleaning. Lastly, they have front-loading seals for easier and faster maintenance. Why legacy AODD pumps fail? Most AODD types are not CIP capable and require manual cleaning. Remember, manual cleaning is the root cause for most pump damage. Traditional designs route the fluid through the sides, requiring pipe work with many bolts or clamps. And this leads to very labor-intensive cleaning. There's also significant product holdup, which wastes product during batch change and maintenance. Updated AODD pump designs allow for both CIP and COP with the same pump. It allows access to the pump internals by removing just one large nut. This saves time during maintenance and cleaning, and we've heard reports from time going from 2 hours to clean down to just 15 minutes. The pumps can also be CIP'd, clean in place with up to 7 bar of pressure. So in the real world, properly following procedures outlined in pump manuals is the exception, not the norm. That's the reality. If the manual calls for torque wrenches to be used, they may or may not be used in reality. So what can you do to maintain or improve performance? Well, you can address the root causes of pump wear outlined here. You can utilize newer pump technology designed to simplify sanitation and minimize pump damage. And remember the golden rule. If you minimize pump damage, you maximize pump performance. I really hope this was helpful for you guys here today. Thank you so much. I appreciate the time. Please visit our website to learn more about new technologies and practices that help you optimize your pumps. Again, thank you very much.
Eric, thank you so much for that great presentation. In just a moment, we'll get to the Q&A session, but attendees, if you would like a certificate of participation for today's webinar, you can access that by clicking the View Certificate button. And if you have questions you haven't sent over yet, now's the time to do so. Keep those questions coming, and we'll keep pulling them from the chat to get to as many as possible. So at this time, let's begin the Q&A. All right, our first question is, how can I reduce damage during COP cleaning?
That's a good question. Let's talk about first what COP cleaning means. That's manual cleaning. And manual cleaning is the standard process in most poultry applications, pet food applications, meat applications, and most prepared food type applications. So in these plants, typically third shift is where sanitation crews come in, and they are notoriously rough on equipment. They have a tough job. They have a very short window to come in there and get everything taken apart, cleaned, and put back together. That's a demanding job on the sanitation crews. It's a demanding process for the equipment. So what can we do to minimize that? We typically say try to simplify the sanitation process. And what do we mean by simplifying sanitation? Well, for example, you can utilize pumps that have fewer components. Not all pumps are created equal for COP applications. One might have 25 components that need to be taken apart for cleaning, whereas another is designed for that process, might only have, say, 4 components to take apart. It goes without saying that the more components you have, the more room there is for error, for things to be broken or misplaced during the cleaning cycle. So simplifying that and utilizing pumps with fewer components is a big step. You can also make it easy and repeatable for the cleaning process. Sanitation crews have a pretty high turnover, so it's not always the same person doing the job. So utilizing pumps that are relatively straightforward with that regard goes a long ways as well. Also, using the right tools. I've mentioned in that presentation that I've seen channel locks be used to pull rotors apart from pumps, and that's obviously not the right tool for the job. Again, there are pumps that are fine-tuned for this that actually enable you to take the pumps apart without the use of tools at all. The less tools you put in the pump, the less damage you get to the pump. And that also goes with better pump handling. It's fairly common to see sanitation crews take a pump apart and throw all the components into a bucket. And stainless steel is very soft. And if you put dings and dents in that stainless steel, that translates to wear and tear and performance loss. So having a good procedure for handling the components when you're cleaning a pump is important. Many plants have, I've seen them come in with stainless steel carts, nice organized carts where they can put all the components of the pump on there, even some hooks where they can hang them for cleaning. And lastly, to use proper torque ratings or torque wrenches when they're putting everything back together, specifically the rotor bolts. This is a big one. Rotor bolts are the leading cause for material being released into a process. And that's due to with a rotor bolt, you can do one of two things. You can either over tighten it over time, or you can under tighten it. Over tightening it can lead to serious damage to the pump, crushing, offsetting tolerances inside the pump, and under tightening it can cause the rotor to back out during production. Both of those are devastating for the pump, and they release foreign material into the process stream. So the best rotor bolt is no rotor bolt. Again, there are pump types out there that are designed for the COP applications and don't use rotor bolts at all and have free floating rotors for that purpose.
Sounds good. The next question is, are rotors for PD lobe pumps interchangeable? Can I put rotors from one pump into another?
No, the short answer is no, you should never interchange rotors from one pump to another. Almost all lobe pumps are hand tuned and get the tolerances perfect inside that pump. Those rotors belong on that shaft in that pump. And I can give you an example of why that's important. Let's say you have one shaft or one rotor that's making contact. It's out of performance, or it's out of range of where it should be, out of tolerance, and it's rubbing in there, causing wear. Well, if they take that pump apart and put the wrong rotor back on the wrong shaft, now you got the other rotor with the tolerances offset and it's rubbing. So now you have two rotors that are rubbing inside that pump, creating wear and tear and performance drop, which usually requires, for most pump brands, remachining. Remachining opens up a world of other problems. Let's say every time you get a pump remachined, you are sold back, they sell you a custom sized rotor that fits into just that pump. And that creates problems if you have a plant with, let's say, 8 pumps of all identical pumps in a COP type application. Well, when they're taking those pumps apart, it's only a matter of time before that remachined pump, or several pumps have been remachined, before the wrong rotors end up in the wrong pump. And when that happens, you get major wear and tear. The pump gets essentially destroyed. You get foreign material, and the cycle of remachining starts all over again. So the short answer is no, don't interchange rotors with other pumps. We know it happens. It happens all the time. But as a pump manufacturer, we always tell them that the rotors need to go back into that same pump, and preferably back onto the same shafts.
Sounds good. Okay, the next question that we have is, how do I know my discharge pressure if I don't have a pressure gauge?
How do you know the discharge pressure if you don't have a pressure gauge? Good question. Actually, it's fairly common to not have pressure gauges inside plants. And the way you can figure out your pressure is you have to do a friction loss calculation. So friction loss is essentially the energy loss that occurs in a pipe when you're transferring that certain product at a certain distance inside that pipe. So to do a friction loss calculation, you need your flow rate, you need viscosity of the product, you need the inside diameter of the pipe, and you need the total pipe length, as well as any kind of vertical rise. So with those 5 components, you can enter that into a friction loss calculator, which are available online, or most pump manufacturers, application engineers have them. And when you type that information out, you will get your pressure, estimated discharge pressure on that line. These are extremely helpful. I highly recommend everyone check their whole process piping on the discharge side with a friction loss calculator.
Sounds good. Everybody, we've had some questions come in about being able to access the presentation later. You'll get an email from us later today, and that'll have a link to the on-demand. So you'll be able to access playback and presentation from this event, and that'll be heading to your inbox soon. All right. The next question is, how do you avoid cavitation of a pump?
So how do you avoid cavitation in a pump? This really has to do with the product you're pumping and a couple other scenarios. And first of all, you want to make sure you have the right size pump. If you remember in the slideshow, there's a golden rule: a pump can't really pump unless you get the product into the pump. So first and foremost, you want to look at the pump's inlet. You want to keep, on the suction side, I should say, you want to keep the pump as close as you can to the supply vessel. You want to minimize the piping from your supply tank over to the pump. Keep that pipe as big as you can and as short as possible without any bends. So straight, short, and big. That's what you want. For example, you don't want to, remember the milkshake with the coffee straw analogy. You don't want a 3-inch pump being fed from the tank with a 2-inch line. That can obviously restrict flow or cause cavitation as an issue. On the downstream side, you want to use a friction loss calculator that we just talked about on the question prior. That'll give you the discharge pressure of your piping. And if you remember the slide where we had a comparison between 2-inch piping and 3-inch piping on the same example, 2-inch pipe on a certain process had 177 psi, versus if you upsize that pipe to a 3-inch pipe, it dropped the pressure down to 32 psi. So to keep it efficient on the pump, always upsize the piping on the discharge if possible, because relieving pressure on the pump is always a good idea.
Sounds good. The next question we have is, which pump is more efficient if the product is viscous? Would it be the AODD or the lube pump?
So I'm pretty sure they meant to say lobe pump on there, but I don't know if you can say one's more efficient than the other. AODD pumps, I can't speak to what their max viscosity ratings are for other brands. I know that Uniblock Hygienic Technologies, our AODD pump, can handle viscosities up to, I think, about 500,000 centipoise, and it can do so fairly efficiently. And also the lobe pumps can handle viscosities even higher than that. Much of this comes back to proper setup. Are you making it easy for the product to get to the pump? Remember, a pump can't pump it if you can't get it into the pump. AODD pumps are much better at pulling product towards them to a certain degree. But generally speaking, if both of those pumps should operate really efficiently if they're set up correctly. You have the right diameter piping, process piping set up on the inlet side, as well as on the managing pressures on the discharge side.
Sounds good. Another question about lobe pumps. What's the difference between a lobe pump and a twin screw pump?
Well, lobe pumps just have typically 2 or 3 lobed rotors that spin, and a twin screw pump has intermeshing screws to push the product. They both work really well at moving viscous products. They both are excellent choices for shear sensitive product transfer. Yeah, they have some differences. The lobe pumps are typically not used to push CIP fluid. Sometimes they are, but twin screw pumps can excel at pushing the product and also push CIP fluid.
Sounds good. Another question says, most times the process will dictate higher pressure or more flow to keep up with demand. How can we make changes to the pump type or size to increase the life and performance of a process pump?
Good question. I would say the biggest thing you can do is sizing the pump correctly to start with. And by that, I mean typically going bigger on the pump. Go for a bigger pump and run it slower. Run it in the middle of the road of its capabilities, or even to the left if you're looking at a flow chart. I have seen that many times where changes on the process piping or product requirements need more flow rate. They want more demand. They get more products, or they have higher pressures. You can also, well, let me back up. Another benefit to going with a larger pump is you get bigger shafts. And the reason that's important is if pressures or as pressures increase, the shafts want to push away from each other. It's called deflection. So higher pressures typically lead to more deflection. And a thicker shaft won't deflect as much as a smaller pump's thinner shaft. The thin shaft's going to bend much more. Think of this as having like a broomstick, a long, thin broomstick, is going to bend a lot more than a shorter, thick one. So going for a larger pump is going to help decrease the deflection inside that pump, which will lead to better performance under the higher pressures. On that note, you can also consider pumps that have bushings in the front that help support those shafts, so the shaft essentially can't deflect. And that'll enable that pump to hit much higher pressures and also get significantly longer shaft seal life.
Sounds good. The next question says, how do I know what line size to go with to maximize performance?
That's essentially the same as the question I answered before, going back to making sure you have the proper inlet and outlet connections on that one. Let's get to that one online later.
Okay, sounds good. The next question says, how can an AODD pump be CIP capable?
Okay. So most food grade or hygienic AODD pumps are CIP capable when the pump itself is pushing the process fluid. The issues generally arise when there is a CIP pump or external CIP pump or CIP skid, and they bypass the pump during cleaning. What can happen on many AODD pump brands out there is that pressure from the CIP process can actually damage the diaphragms. They're not really built to handle very high pressures when it comes to CIP cleaning. And that can lead to, that actually causes them, for the most part, these pumps to be manually stripped down and cleaned. So even in a CIP application, because the diaphragms can get damaged from the CIP pressures, they require, in most instances, these AODD pumps to be manually cleaned. And again, when you're manually cleaning the pump, now you're opening it up to all the dings and dents and damages that occur and lost components in that whole COP process. So there are some AODD pump brands out there that offer backing plates to support the diaphragms, and this allows you to handle much higher CIP pressure. So the pump is a true CIP-able pump. You don't have to take it apart. It can handle cleaning pressures up to 7 bar or about 100 PSI.
Sounds good. The next question says, the lobe has suction power. Why not?
I'm not really understanding it, but generally speaking, lobe pumps are designed to push. They really don't want to pull very much. That's just the nature of them. Lobe pumps do pull a little bit when they're primed. So that's why it's so important to make sure you have efficient infeed to pump. You have to get that product into the pump. It's just the nature of how a lobe pump is designed. Some rotor classes are better than others. If you're pumping like a cold product, you can get much tighter tolerances inside your rotors, which will provide a little bit better suction, but the pumps are never really designed to do that. They're designed to push, not pull.
Sounds good. The next question says, what size strainer do I use to protect my pump from foreign material and damage?
Strainer and damage. So strainers, to protect the pump, you want to put the strainer obviously upstream of the pump. And that only works if the product allows for you to use a strainer. Again, if you're pumping like a thinner product or like a beverage or something like that, then a strainer will work just fine. If you're pumping like a chili or a soup, then obviously a strainer would just get clogged up immediately by the product. But one key thing to consider when you're putting a strainer upstream of a pump is you want to avoid pressure drop from that strainer, because it takes energy to push the product through that strainer, and you don't want to do that. You don't want to rob energy from the inlet side of a pump. So what we recommend there typically is going with as big of a strainer as you can find. So for example, our line of strainers that we have, you have a 2-inch strainer that can have 3 or 4 different sizings options of the actual housing. And the larger the housing, the less pressure drop you have for that product to go through there, which makes it nice and efficient to get through the strainer. and not cavitate or pump or deprive that pump of product. So basically on the strainers, it kind of follows the same rules with the pumps. Go as big as you can. On the strainer housing, it's almost always a good idea. A larger strainer housing is going to have less pressure drop and also catch more foreign material and longer instances, between cleaning. If you have a lot of product, it gets clogged up in there.
Sounds good. The next question is, what is the max viscosity you can pump?
Again, I'm not really sure on other brands. I can only speak to the Uniblock brands. But on the AODD front, we can pull suction lift up to with like out of a tote or a drum with a lance. You can pull suction lift up to 30,000 centipoise. We can pump up to 100,000 centipoise in a flooded tote, or we can go up to 500,000 centipoise on our drum unloaders. So the 500,000 is the max on the AODD pump. On the lobe pump front, we can go up to we've done up to 1 million, actually over 1 million, but we say 1 million centipoise is the max viscosity on a lobe pump. But we actually have an example of this. We did a fruit filling for a very popular candy bar manufacturer, and that product was actually over 1 million centipoise. And what we did for success there was we had an oversized pump with a very large inlet, and we ran that pump extremely slow. I believe that pump ran at 8 RPM, so 8 revolutions per minute, and it worked well. So, but when you get up to those really, really high viscosities, there's other challenges that come into play. A lot of times for higher viscosities, we recommend going to a rectangular flanged inlet for the pump versus like a round tri-clamp. A rectangular flanged inlet is going to make it much more efficient to get the product into that pump so you can pump it. But you also have other issues like product bridging. Once the viscosity gets that high, bridging is when the product basically blocks itself from falling down into the pump. Chicken, we do a lot in the meat industry, and chicken bridges all the time. And that can be due to poor hopper design. A lot of times, if the hopper has relatively obtuse angles like this, then the product can't feed, doesn't get pushed down as much as if it were a very steep-sided hopper. The steep-sided hoppers help force that in. But even then, if bridging is a concern, or if you can't get the product into the pump, then you want to consider using like an auger feed system, something that helps force feed that product to the pump, and then you can pump it wherever it needs to go.
Sounds good. Well, everybody, that does it for our webinar today. If we didn't get to your question, we'll get it to Eric and the Uniblock team so that they can answer it offline. Attendees, like I mentioned before, you can look from an email for us later today where you'll be able to access playback and presentation from this event. But please also feel free to visit pumpsandsystems.com for more on this topic and for additional educational webinars. Thanks again to Eric and the Uniblock Hygienic Technologies team, and thank you to everyone for taking the time to join us today. I hope you have a great day.